Okay, let's dive into this. Have you ever actually stopped to think about how your digital devices feel the real world? Like, how does a computer actually know it's hot outside or that you just pushed a physical button? Well, in today's explainer, we're going on a seriously fascinating journey. We're going to trace the exact, literal path of a signal. We'll start from a raw physical phenomenon, like heat or pressure, and follow it all the way through its transformation into the digital data that powers our entire modern world. It is an absolutely incredible process of translation, and it's happening millions of times a second all around us. We've got a really great roadmap for this journey today. We'll start with sensing the physical world, then move on to making it micro with MEMS. After that, we'll bridge the gap between analog and digital, dive into data acquisition systems, and finally, look at how the PC acts as the ultimate brain. All right, Section 1, Sensing the Physical World. This is step 1 on our journey. It begins right at the point of contact with the environment. It's where reality quite literally meets technology. So you hear the word sensor all the time, right? But the crucial thing here is understanding the difference between a simple sensor and a transducer. While a sensor just detects a physical change, like, say, a shift in temperature, a transducer goes a step further. It takes that detection and actually conditions it into a usable electrical signal. Basically, a transducer is a sensor combined with a signal conditioning circuit. It's the whole shebang, making it a much more comprehensive tool for gathering data. To put that into perspective, think about a heat flux transducer. Imagine a device designed with a specific filling of constantan and copper. What this does is measure the exact rate of thermal energy transfer across a surface area. So, as heat flows through it, the temperature difference generates a voltage signal that is directly proportional to that heat flow. It's quite literally turning warmth into electricity that a machine can read. How cool is that? Or consider a strain gauge. This tiny metallic pattern is an absolute workhorse in the engineering world. It acts as a foundational element for measuring force, pressure, and torque. And the way it works is so elegant. When physical force is applied, the material stretches or compresses. The gauge then converts that tiny, microscopic displacement into a measurable change in electrical resistance. It's a simple concept, but it's incredibly effective. Because they are so effective, these electronic nerve endings are everywhere. I mean, they're driving critical systems across virtually every industry you can possibly think of. We're talking everything from GPS navigation helping guide satellites in space, to complex environmental networks monitoring the air quality in your city, to modern agriculture and aviation. They are the eyes and ears of our entire global infrastructure. Moving on to Section 2, Making it Micro with MEMS. Let's see what happens when we shrink these incredible sensing capabilities down to a scale we can't even see with the naked eye. Welcome to the microscopic world. Now, to really appreciate the engineering leap here, you have to compare standard microchips, regular integrated circuits, to micro-electromechanical systems, or MEMS. Standard chips are mostly two-dimensional, stationary things securely locked away inside protective casings. But MEMS, these are complex, three-dimensional structures with actual, moving microscopic components, and they're designed specifically to physically interact with their environment. Because they're built to physically touch the real world, they require entirely distinct custom manufacturing techniques. So, how do you even build microscopic machines like that? Well, engineers use a fascinating process called photolithography. It literally uses light to carve materials. First, they coat a flat substrate, like a silicon wafer, with a light-sensitive material called a photoresist. Next, they expose it to light through a highly detailed quartz mask. And finally, the areas exposed to that light change their chemical solubility. This allows engineers to wash away highly specific parts and leave behind perfect, microscale 3D geometry. It's like developing a photograph, but you're building a machine. If you were to slice one of these open, say a micropressure sensor, you'd see the direct result of that photolithography process. You'd find a tiny, etched physical cavity with piezoresistors placed precisely on top. When microscopic pressure enters that tiny passage, the incredibly thin silicon layer flexes, and the piezoresistors measure that flex. You're looking at a functioning mechanical machine that is smaller than a grain of sand. Which brings us to Section 3, Bridging Analog and Digital. So we've got our raw, tiny electrical signal from our microsensors, but now we hit a major translation problem. We have to translate it into a language a computer can actually understand. Enter the signal conditioning circuit. Think of this intermediate circuit as the spinal cord of our system. The raw voltage coming straight out of a sensor is often tiny and just full of environmental interference. the signal conditioner steps in to filter out that unwanted noise and amplify the raw data. It basically makes the signal clean and strong enough before it ever reaches the computer's brain. The ultimate goal of crossing this bridge is to fundamentally change the format of the information. See, the physical world gives us analog signals. These are continuous, smooth, wavy lines that represent shifts in things like voltage or pressure over time. But our digital systems, they can't read continuous waves at all. They need discrete data. So the system chops those continuous, wavy analog signals into discrete, discontinuous digital pulses. Basically, choppy highs and lows, ones and zeros. All right, Section 4, Data Acquisition Systems. This massive transformation brings us to the central hub where all these conditioned, digitized signals finally converge. We call it the DAS. Imagine tracing the path of an entire factory's worth of sensors. You start with multiple physical transducers, maybe measuring temperature, pressure, and flow all at exactly the same time. They each feed their raw data into their own signal conditioners to get cleaned up. Then, all those separate, distinct signals are routed together into one single powerful central processing stream. To handle all that incoming traffic efficiently, the system relies on a multiplexer. The multiplexer is essentially the traffic cop of this whole setup. Instead of buying a separate, highly expensive digital converter for every single sensor in a huge industrial plant, the multiplexer sequentially grabs data from various sensors and funnels it into a single analog-to-digital converter. It switches between them so insanely fast that it effectively monitors everything at once, which massively reduces both hardware and installation costs. And finally, we hit Section 5, the PC as a brain. Our clean, amplified, digitized, and multiplex signal has finally arrived at its destination. At this stage, the personal computer takes total control. The PC acts as the true brain of the operation. It uses specialized hardware and software to perform incredibly complex arithmetical manipulations. It basically takes this absolute fire hose of digitized numbers and turns it into something a human operator can actually see, understand, and make decisions with. And with the data now fully digitized, the capabilities of this PC brain are just staggering. It can run high-speed digital signal processing for instant analysis. It can generate these brilliant mimic displays, which are intuitive visual layouts on a screen showing operators exactly what's happening at specific physical locations in a plant. It can even simultaneously plot multiple parameters to track historical trends, easily handling massive industrial environments without breaking a sweat. As we wrap up this explainer, tracking this journey from a raw physical force to a digital insight on a screen, it really makes you pause, doesn't it? We've seen how heat, strain, and pressure are captured, conditioned, and completely digitized. If a microscopic machine etched into silicon can translate physical reality into digital intelligence with such wild precision, well, it makes you wonder just how much invisible information our physical world is constantly broadcasting around us right now, just waiting to be measured. Keep that in mind the next time you look at a digital dashboard. Thanks so much for joining me today.